Don't use Taylor expansion to find this series. So basically in this video I will try to find the expansion for these functions. I will first try to show you like how or why it's difficult to use Taylor expansion to find their series, and what's the best way that we can use to find this series. Okay, so basically let me show you like why it's difficult. So let us take f of x equals to arc sin x. Yeah, and let us try to find its series using the definition of Taylor expansion. That the definition is the expansion of f of x and centered it around a, centered at a. Yeah, that means center of convergence is a. So in that case, the expansion will be f of a plus f dash a x minus a by 1 factorial plus f double dash a x minus a whole square by 2 factorial, and this goes on. Yeah. Now if you want to center this expansion around 0, yeah, if you want to center this expansion around 0, that gives us the Maclaurin series, and that will be f of x equals to f of 0 plus f dash of 0 x by 1 factorial plus f double dash of 0 x square by 2 factorial, and this goes on. Yeah. And for radius of convergence we need to find it out by ourselves. Yeah, the series does not like guarantee what the radius of convergence is. Okay, now let's try to find its expansion using the Maclaurin series. Yeah, first of all our f of 0 will just be 0, yes, since arc sine of 0 is 0, and then our f dash x will be 1 by root under 1 minus x square. Yeah, and when you put 0 over here, this gives us 1. Yeah, and now uh, this is 1 minus x square to the power minus 1 by 2. Now we can definitely find f dash x. That will not be a lot hard. Yeah, yeah, that will not be a lot hard thing. Minus 2x, and nicely minus 2 and this cancel out. We have x times 1 minus x square to the power minus 3 by 2. Okay, so now if we put 0 over here, f double dash of 0 will just be 0. Now till now it's easy. Now if you go to triple derivative, we'll basically have to use product rule. Yeah, and again like from this expression you will again get another product. Now in fourth derivative, that will be a complete maze. Yeah, so that's why like if we try to use this definition, we will not be able to find like f fourth of x or f fifth of x. That will be a complete trouble. So we might not be able to find the complete expansion for arcsine x. That's why we will try to find some other ways to find the series, and the other way is something like this. So basically what we can do is we can try to find the expansion for its derivative. Yeah, okay, so its derivative is 1 by root under 1 minus x square. Now if we have the expansion for its derivative, we'll just integrate both sides. Yeah, and then uh, we will have sine inverse x over here. Yeah, and now the series, we can integrate the series part by part, and you will have a new series and plus c. Yeah, and in this way we can get the series expansion by integrating. Now I will try to show that for arctan of x first, since this one is a bit easier, and then we will go to other two. So basically for arctan of x we will try to use its derivative, which is 1 by 1 plus x square. Now to find the series expansion for this, we know that this is 1 by 1 minus x square. Now this is in the form a by 1 minus r. Now if modulus of x is less than 1, modulus of minus x square will also be less than 1. So in this case we can find the series expansion. Yeah, and this has radius of 1 and center at 0. So the series will be sum from n equals to 0 to infinity minus x square to the power n and 1 over here. First term is 1, and the in our uh, the ratio is minus x square. Yeah, so this is the series expansion for this term over here. Now if we integrate both sides, from here we get tan inverse x, and from here we get, we can just take integral inside the summation, and we get sum from n equals to 0 to infinity, minus 1 to the power n x to the power 2n plus 1 by 2n plus 1, and boom, we got the series expansion for tan inverse x. Now the thing is, we need to find the constant. Yeah, for that we can just substitute x equals to 0 in the expression. From here we get 0, from here also we get sum of 0 is 0 plus c, and that leaves us with c equals to 0, so we can just remove the c in fact. Yeah, so in this way we get the series expansion, and the center of convergence will just be the same as that of the previous function, previous series. So center will be 0, and radius will again be just be 1, and endpoints of the radius needs to be found out again. So this is how we can find the series expansion without using the Taylor series. And now let's proceed to the other ones, arc sin x and arc cos x. So arc sin x, the derivative of arc sin x is uh, root under 1 minus, sorry, 1 by root under 1 minus x square. So this is the derivative of arc sin x. Yeah, this can be written as in this form. Now we can use binomial expansion to expand this. Okay, and the binomial expansion says that binomial expansion for 1 plus x to the power n is sum from k equals to 0 to infinity n c k, or in other way I can write this as n k and then x to the power k. Now if I'm wondering why I wrote over here infinity and not n, because infinity is a kind of a general case. Infinity, if we write infinity over here, like it will also include the cases where n is an integer, or let's say positive integer, and also when n is a fraction. Now let me show you how it includes the case of uh, positive integers as well. So if we have to find this expansion, basically what this says is we will first have uh, n c0. So basically that will just be n, is that, or no? Okay, no, basically 1 c0 is just 1. Okay, so that means we will just have nothing. Okay, 1 times x to the power 0, is that okay? Fine. Now nc1 is basically 2 by 1. Yeah, so basically let me like take some other integers, I mean general integral other than this. Okay, basically let me take n itself, where n is a positive integer. Let us see in that case. So first will be 1, and second will be n by 1 factorial x, and third will be n minus 1 by 2 factorial x square. Yeah, and then we can take it as n minus 1 n minus 2 by 3 factorial times x cube. And if it goes on like this, yeah, basically now n minus 2, and if it goes on, basically we'll reach a point where we will have n minus 1. Yeah, in that case we will have by 1 factorial to the power x to the power n minus 1, is it? So in this case, okay, no, basically when there's 2 we have x cube, so we will have x to the power n over here. Now after this, if we are going up to infinity, what we get is n minus 1 n minus 2, and it goes on, and n minus 1, and then we get n minus n, yeah, and by 0 factorial to the power x to the power n plus 1. So in this case, since we have n minus n over here, like this goes to 0. Yeah, and again, even in the next term also, even in the next term also, n minus 1 n minus 2, it goes on, and we will have n minus 1, and then n minus n, and then we will have n minus n plus 1. Yeah, And in that case, we will have minus 1 factorial. We don't know what this is though, and then x to the power n plus 2. But since here's a 0, this will go to 0 again. So basically, even if we continue to infinity, all of these terms are going to 0. And basically, for integer, what remains is this series expansion, which is just sum from k equals to 0 to n c k x to the power k. Yeah, okay. So this is what it is. So basically, I can write this as this sum as general expansion of binomial. So yeah, and for integers it comes out that this sum is equals to the one over here, but for fraction powers it is not equal to. Now let's go over here. We have that deal, and now we have sum from k equals to 0 to infinity. Over here n is minus 1 by 2. We have minus 1 by 2, choose k, and then we have minus x square to the power k. Yeah, and now for this sum minus 1 by 2 choose k. So what that means is we will just keep on like subtracting 1 and 2 and so on. And in the kth term, since in second term we are subtracting minus 1, in third term we are subtracting minus 2, so we will go up to kth term, and in kth term we will subtract k minus 1. Yeah, by this is k factorial, and then we will have minus x squared to the power k. So this is the sum. Now we can neatly write this in the following way. So basically, since there are k terms, we can take minus 1 common from each of them, and we get minus 1 to the power k. Yeah, and then we can take 2 in the denominators. We have k terms, so 2 to the power k will be there. And if we take 2, yeah, in that way, we have 1 times, this is 3 times, and this will be 5, 7, and if it goes on. Now over here we will have 1 by 2 plus k minus 1. So that's 2k minus 2 plus 1, so that's 2k minus 1. Is that? Yeah, okay. And then we have minus 1 to the power k over here, and x to the power 2k. Yeah. Now after this, what we can do is, so basically we have 1 to the power k twice, so that is 1 to the power 2k. Sorry, minus 1 to the power 2k. And now this can be written as 2k factorial by, so basically we are adding 2, 4, 6, 8, 10 and so on up to 2k. So basically we are adding like k factorial times 2 to the power k. Yeah, basically those we can take 2 common out from all those 2, 4, 6, 8, 10 and so on. And if we take 2 common out, we will basically have 2 to the power k common out from all the expressions, and as well as we will have 1, 2, 3 as well, so which is k factorial. So basically this expression over here will be 2 to the power k times k factorial common out, and also we already have one such thing, 2 to the power k times k factorial. Yeah, and then x to the power 2k. Now we have sum from k equals to 0 to infinity. This will just be 1, and we will have 1 by 4 to the power k, and 2k factorial by k factorial is just 2k choose k, 2k combination k, and x to the power 2k. So this is finally the binomial expansion for okay, so this one 1 minus x squared to the power minus 1 by 2. Yeah, sum of 1 by 4 to the power k, 2k choose k by x to the power 2k. So now after we have this, it's not that hard to find the series expansion, series expansion for sine inverse x or arc sine x. After this, what we need to do is, so this is for 1 by 1 plus x square. Now if we integrate both sides, yeah, we will get, root also, we will have arc sine x is equals to sum from k equals to 0 to infinity. Yeah, and then over here we will have 1 by 4 to the power k 2k choose k. These are just constants, so no need to do anything. And over here we will have x to the power 2k plus 1 by 2k plus 1 plus c. Yeah. Now if we put x equals to 0, our left hand side will just be 0 and right hand side will be, since x is 0, we will just have sum of zeros, which is 0 plus c. So that's why c is also equals to 0, and so we can remove the c. Yeah. And yeah, this is the uh, series expansion for arc sin x. And since our original series is centered at 0, this will also be centered at 0. Yeah. And next thing is radius will just be 1, as in the earlier expansion. Since the original expansion has uh, since the binomial expansion formula, yeah, even the binomial expansion formula for like fractional powers, so this is basically convergent for modulus of x less than 1, so that's why that will be carried on to the new series as well. So this was for the arc sin x. Now for like arc cos x, it will not be that hard, since we know that arc cos x plus arc sin x is just pi by 2. And if you want to see how, you can just draw a right angle triangle. Yeah. Yeah. And basically now the arc cos x, now basically let us name these as ABC. Yeah. And now okay, so this will be p b s, and let this be theta. Okay. Now if you are taking arc cos x, uh, what we will get is, so basically let the x for now be p by b. Yeah. And in that case arc cos x will just be what, sorry, let us take x as b by s, so we can take anything. Yeah, arc cos x will just be this theta, and arc sin x will just be this alpha, because for theta, like cosine is b by s, so arc cos x will be this theta, but for alpha, b by s is sine. Yeah, so arc sin x will just be this alpha, so this is basically theta plus alpha will be there for this case, and that's pi by 2. This is one of the visual proof, but you can also other proofs. Yeah, doesn't matter. And now after this we have arc sin x as pi by 2 minus arc cos x. Yeah. And so using this we can find the series expansion for arc cos x. Yeah. And okay, so basically I wrote it wrong. Basically I mean to say that arc cos x equals to pi by 2 minus arc sin x, and now we can just substitute the series expansion of arc sin x over here, and that will be the answer. So which is what I have done over here, just substitute the pi by 2. And yeah, now we have found a series for all of these, and we didn't use the definition of Taylor series. We in fact integrated the other expansions that we got from geometric series, binomial series, and yeah, that did help us solve the problem. I hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the upcoming videos too.